Nathan, Nathan, Nathan. Nathan, 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 Nathan. N-A-T-H.
In this series of videos, I'll discuss section 7.5 of Stewart's book, Strategies for Integration. There's not any new material in this section. It's really more of a review. And the idea is that on midterm 2, you should expect to see some integrals. And you won't be told what technique to use to compute those integrals, so you'll have to decide, what should I try? We have all these different ways of computing integrals, and we want to know how should we think about what techniques to use at different points. So in this first video, what I want to do is remind you of some integrals that you should see and immediately think, I know that one. I don't need to try any techniques. I can just write down the integral immediately. So what I have here on the whiteboard is taken from this chart on page 503 of Stewart's book. I highly recommend that you check it out. And it's just a list of integrals that you should know. Let me first point out that these are all indefinite integrals, so they really should all be the integral of f of x dx equals some antiderivative plus c. But we're leaving out the plus c everywhere just for reasons of space and clarity. All right, so what's the first one? Well, one of the first functions that we talked about was the integral of x to the n, like the integral of x squared, or the integral of x to the 7th, or the integral of x to the 0, which is 1. And using the power rule for differentiation, you can see that an antiderivative is x to the n plus 1 divided by n plus 1, because the n plus 1 comes down and cancels out, and you get x to the n. That works for every real number n, except n equals minus 1 is a special case. We saw separately that the integral of 1 over x is equal to the natural log of the absolute value of x. And the absolute value is important because we want the domain to be as large as possible. Okay, a next type of integral that you can see and recognize how to do is the integral of an exponential function. The integral of e to the x is e to the x, because e to the x is its own derivative. What about if you replace e with some other number a, the integral of a to the x? Well, what you get as an antiderivative is 1 over natural log of a times a to the x. And remember, for this to make sense, a should be greater than 0. So how do you remember that that's true? I find this useful to go over. A to the x, another way to write it is it's e to the natural log of a, that's the number a, raised to the x. And then when you have one number raised to another, you get the product of those two exponents. You get the first number raised to the product of the two exponents. So here, we get e to the natural log of a times x, and now taking the derivative, applying the chain rule, you get natural log of a times a to the x. So that's how to remember what's going on, because now when you take a derivative here, you get a natural log of a that cancels the 1 over natural log of a. Okay, next class of integrals that you should look at and think like, oh, I know this one, are integrals of trig functions. The integral of sine of x dx is negative cosine of x. The integral of cosine is sine. The integral of tangent, this was a good one that we did with u substitution. It was one of the very first examples we did with u substitution. Tangent is sine over cosine. So if you let u be equal to cosine, then what you have in the numerator is negative du. So what we get is natural log of absolute value of cosine times negative 1. And using log rules, you can rewrite this as natural log of absolute value of secant of x. So this is a good one to know. This comes up all the time with all of the trigonometric integrals, the trig subs, things like that. Okay, continuing along this type of example, the integral of secant squared is tangent, because the derivative of tangent is secant squared. The integral of secant times tangent is secant, because the derivative of secant is secant times tangent. So these you should recognize right away. In the partial fractions 7.4 videos, we talked about the integral of 1 over a squared plus x squared dx. So there we got 1 over a times arctan of x over a. Right? The main idea is that when a equals 1, we know that the derivative of arctan is 1 over 1 plus x squared. And if you sort of divide out a factor of 1 over a squared and then let y be equal to x over a, you can get this expression. Okay, another one. So we know the derivative of arc sine is 1 over square root of 1 minus x squared. So using that fact and doing a similar thing to the above example, we can see that the integral of dx over square root of a squared minus x squared is arc sine x over a. And again, for this to make sense, we want a to be positive. And the last one that you should know is the integral of secant. This one is tricky. The idea was to multiply this function secant by secant plus tangent over secant plus tangent, and then apply a u substitution with u being equal to the denominator. And what you get is natural log of secant of x plus tangent of x. I'll point out there are a few other things that come up in the chart in Stewart's book, things that involve like cosecant and cotangent. And let me tell you that I don't have all of the derivatives of those kinds of trig functions memorized. I don't have all of those integrals memorized. But you can do the integral of cotangent just like we did the integral of tangent. So if you remember how to do the integral of tangent, you don't need to memorize the integral of cotangent. And for things like derivatives involving cosecant, that's similar to integrals involving secant. So for derivatives, you can figure them all out using the quotient rule and the derivatives you do know. And then for integrals, the ideas are similar to the ones we've seen here. So these are building block integrals where you see an integral like this and you think, aha, I know that one, and you shouldn't really have to apply techniques. You should just be able to answer the question. So in the next video, I'll talk about the strategies for integrals we've gone over so far and how to decide which strategy to try when you're faced with a new integral.